So today we want to talk about the big idea about power series. Think about where do power series come from. So there's a couple of things that we can do. What we want to recognize first is that a power series can be used as a description of a function. A power series can be used as a description of a function. A power series can be used to describe a function. Now, this might seem at first inconvenient because a power series is infinitely long, and that's a lot to work with. This infinite number of terms business must get in the way of its usefulness as a description for a function. But the form of a power series is that of a polynomial. So we can just stop writing and have a polynomial approximation for a function. So the important part of the power series is that its form is that of a polynomial. So the thing that we like most about power series is that it is the form of a polynomial. We get an approximation if we just stop writing terms. We can improve the approximation by writing more terms. We get an approximation if we stop writing terms. We improve the approximation by writing more terms. And this very much fits into the calculus mindset. The calculus mindset is find a way to approximate what you want, and then find a way to do that infinitely. Figure out what you can do to approximate what you're looking for, and then do that forever. And then, of course, the actual calculus thinking, think about what happens if you do this forever. So this is very calculus thinking. So a couple of things that happen that we do with power series. One is we take an existing function and create the polynomial approximation for it. So sometimes we'll take an existing function and write a power series. An example of this is a Taylor series, which is just a higher degree form of the tangent line. A Taylor series is just a tangent line where we keep going. Instead of limiting ourselves to the best first degree approximation, we go for a second degree approximation, then a third, then a fourth, then a fifth, then we just continue on towards infinity. So one of the major things that we go for is the Taylor series. The 0 and first degree terms of the Taylor series tell us about the tangent line, and we just take that process and keep going. So there's an example where we're taking a known function and writing a power series for it. Another thing that might happen is that we have an unknown function, and we use whatever description we have for an unknown function and write a power series. So we don't know what a function is, but we have some description of an unknown function. And we use that description to write a power series. An example in this category is if we start with a differential equation, we can write a power series as a solution. A differential equation is just a description of a function based on the function itself and its derivative. An equation involving a function and its derivatives. And we could propose a power series as a solution if we don't know what the function should look like. Then we just use the power series to evaluate what we want to evaluate, or we recognize what the power series represents. So the important thing is that we have a very simple form that's a polynomial, and we can use it to describe functions. Since this can be used to describe functions, we have to know about it. All right. Because it's Thursday, I want to do a thing that we should not do. And that is write the series solutions in different equations. Just by like, it's not something that you're going to ever have to do. It's probably something it's ill-advised to do. You shouldn't be doing this. I'm going to start with something simple, like y prime is equal to k times y. And we are going to pretend that we don't recognize that the solution to this differential equation is some constant times e to the k times t, or e to the k times x. So we're going to pretend that we don't know what the solution is. This is just a description of exponential growth or exponential decay. Here's a description of exponential growth. The rate of change of a function is proportional to the value of the function itself. So as the function increases, the rate of change also increases. We know that this describes an exponential function. That's like the defining characteristic of the exponential function in terms of it. We're going to pretend that we don't know what the solution is. We're also going to pretend that we don't know how to solve by separating the variables. We're going to pretend that we don't know anything. So we're just going to guess at a solution. So we're going to guess at a power series solution. So we're also pretending that we don't know to separate the variables. We're going to guess a power series solution. That is, guess y is equal to c0 plus c1x plus c2x squared plus c3x cubed, and so on. We're going to take this guess and plug it back in because that's all we really ever have to start with in math. Guess and then check. Now, what we're looking for are the values of C0, C1, C2, and C3. That's what we're trying to find. So in this scenario, we are trying to find the coefficients C0, C1, C2, etc. Once we figure out what those coefficients are, then we're able to build our power series solution. Then we're able to approximate the solution to this differential equation. This is what it looks like when we say, I wonder if the answer is 3. Then we check. It's like, oh, no, we need something bigger than 3. I wonder if the answer is 4. Nope, we need something less than 4. I wonder if the answer is 3.5. Nope, we need something bigger than 3.5. And then just doing that. So y is going to go in for this y over here. I need to know y prime, so I could plug that into the function as well. So I need to write y prime. So y prime will be C0. The derivative of C0 is 0. The derivative of C1x is C1. The derivative of C2x squared is 2C2x to the first. The derivative of C3x cubed is 3C3x squared. And the derivative of C4 is 4C4x cubed, and so on. There we made a guess. Now we check by plugging it back into the equation and seeing what happens. Y prime is this orange series here. So my equation, I'm not going to have to say it. So all we're going to do is plug y and y prime into the differential equation. My differential equation is y prime is equal to k times y. So I'm going to write down y prime, which is this orange series, this is equal to k times y, which is this blue series, my original guess. Plug those two in to the differential equation. This is what my equation looks like. That orange stuff is the y prime, the blue stuff is y. Over on the left, I have power series. Over on the right, I have some other power series, and we are claiming that these two series are the same. That means that the coefficients have to be equal. So now we're going to equate the coefficients. That means if these power series are going to be equal, then the corresponding coefficients must be equal. So note that in this equation, we're not solving for x. That wasn't our goal. We're not saying what x makes this true. We're saying what values of C0, C1, C2, and so on make this an identity. And so that requires that the corresponding coefficients must be equal. Overall, so that means that the constants must be equal. On the left, I've got C1. And on the right, I've got K times C0. Our X terms must have equal coefficients. On the left, the X coefficient is 2C2. And on the right, I've got K times C1. Our X squared terms must be equal. On the left, I've got 3C3. And on the right, I've got K times C2. Our X cubed terms must have the same coefficients. On one side, I've got 4C4. And on the right side, I've got K times C3. Because this one is very straightforward, we can say in general, if I have, what do I want this in terms of, n or n plus 1? Well, let's go with our original. Over on the right, when I have K times Cn, the corresponding coefficient on the left will be one more than that. So Cn plus 1 times n plus 1. This is the thinking behind it. I've made the equation by just guessing a power series solution, plugging the power series and its derivative into the original equation, then trying to equate the coefficients. Now, here's what we find out. Now, this first one says that C1 is K times C0. What this means is I could write every coefficient in terms of C0. So once we have this C1 is equal to K times C0, C2 is K times C1, I can write all of my coefficients in terms of C0. That's going to allow us to factor the C0 out and see what's going on in the rest of the series. So what I mean is that if C1 is K times C0 and 2C2 is K times C1, I can plug KC0 into the C1 so that 2C2 is K times C1, which is K times C0. So we get C2 is K squared over 2 times C0. Since C2 is K squared over 2 times C0, I could plug that into the equation we have involving C3. So then I plug that into the next one. 3C3 is K times C2, but C2 is K squared over 2 times C0. And that tells us that C3 is K cubed over 6 times C0. The next equation says 4C4 is KC3. So I can take 4C4 and write that as K times C3, which is K cubed over 6 times C0. So C4 is K to the 4th over 24 times C0. Now we can see the exponential part happening in K, and we can see the factorial part happening in the denominator. I forgot this is the one that I want to solve for. So I guess NCN will equal K times Cn minus 1. So that's the one I actually wanted. So if N in general, NCN is K times Cn minus 1. Now I'm not going to write it. I usually get it backwards when I teach this class at 8 o'clock in the morning, so I'm not even on time. So now I know what all the coefficients are in terms of C0. So my equation, or my power series solution looks like y equals C0 plus C1 times x plus C2 x squared plus C3 x cubed plus C4 x to the fourth. So at this point, we're able to factor out the C0. And we're left with 1 plus kx. Here I have k squared and an x squared. And k cubed and x cubed. So I'll write kx cubed. And this 6 is going to be 3 factorial, just like this 2 was 2 factorial. Then this fourth power one is kx to the fourth. 24 is a 4 factorial. And we can see where this will go from here. We have enough information now to see what the pattern is going to be. The next term will be kx to the fifth over 5 factorial. We're now at the point where we could speculate. We've got a polynomial approximation for the solution to the differential equation. And so what we're looking at here is the Taylor series for e to the kx. The idea is that we're supposing that we have a power series solution and just making that power series solution fit the description of the function. We now have 3 different ways to describe the function e to the kx. We can say it's a solution to the differential equation y prime is equal to k times y. It is the power series 1 plus kx plus kx squared over 2 factorial, kx cubed over 3 factorial. Write it in a more familiar form, we can write it as a power series since all the terms have the same form. We could think about where this power series solution would be useful. What is the domain of this power series? The numerator has this k to the n, indicate a center of 0 and a radius of 1 over k, but that n factorial in the denominator that goes unchallenged in the numerator means that it looks like the limit from the ratio test is going to be 0, which is always less than 1. So this power series converges for all x. Now, if we use this as an approximation, eventually, of course, it will break down. It won't go on forever because polynomials are still going to be polynomial things. When x goes to negative infinity, the polynomial will eventually want to go to infinity if we stop at an even power, or to negative infinity if we stop at an odd power. Whereas the exponential function e to kx will want to go to 0 as x goes to negative infinity. So the further we are from x, the more terms we're going to need to make this approximation work. But if we are close to 0, we are not going to need a lot of terms. Questions? Comment? Slide along. Our big project next week is to look at Taylor polynomials and Taylor series. This is chapter 10, which is the last chapter where we do the full chapter before we get into selected topics from chapter 11. The big idea with the Taylor series is we first start with Taylor polynomials, and y'all already know your first degree Taylor polynomial. So this is what next week is about. Hey, remember that tangent line stuff from Calc 1? Yeah? Well, just keep going. It's the same thinking, but keep going. The tangent line is the best linear approximation for a function near a point. What that means is that we're making a line that goes through the same point. It has the same value, the same 0th derivative, and is going in the same direction, has the same first derivative at that point. Just keep going. Now make a quadratic with the same second derivative at that point. Now make a cubic with the same third derivative at that point. And so on forever. Because that's what we do in calculus. We find a way to approximate something, and then we just do that forever. That's why tangent line seems so weird in Calc 1. So I call, dude, Calc 1 thinking is about finding an approximation and then doing that approximation forever. Well, now we get to close that loop on our tangent line approximation. All right, so next week we'll talk about Taylor series, but that's going to do it for this week. I will see you all on Monday. Everybody have a good weekend, and thanks for playing. I think I missed an example somewhere, which is why we're done so soon. There's an example that's going to be at least like a 10-minute example, and I just don't know what it was. All right, that's it for today. I'll see y'all on Monday. Everybody have a good weekend. Thanks for playing.